Okay, so our second speaker of the day is Sam Patrick. So Sam did his PhD at the University of Nottingham before moving to Canada to take up a postdoc position at the University of British Columbia. And now he's back in Nottingham, couldn't get enough of it. So he's back there as a postdoc. And we'll be talking about the origin and evolution of multiply charged quantized vortex instability.
Thank you. Okay, so August basically just spoke about wave dynamics following the decay of a very large vortex into a cluster of vortices. So in his talk, he referred to this as the stage 2. Now I'm going to be talking about what he called stage 1, which was, or really just following stage 1, which is the dynamics of the system during this vortex decay. So what's really causing this vortex decay. So I'd just like to point out that this is based on some work by the same group of people that wrote the paper that August just spoke about. And here's the archive link at the bottom if anyone wants to look into this further. So just here on the left-hand side, it's a brief summary of how this is going to go. I'll first start by introducing a much simpler system than the one that August spoke about. We're going to be focusing on vortices of much smaller winding to make things simple for ourselves. I'm going to argue that this vortex decay stems from an instability of the linear equation. So I'll then introduce the linearized equations of motion. I'll then present some simulations of this decaying vortex, and there we're going to encounter some very interesting, unexpected behavior, which is really the point of this talk. And then I'll just wrap up by summarizing. So first of all, we're thinking about a much simpler system. We're going to have a single vortex in the center of a bucket-shaped trapping potential. And the reason that this is simpler is because we're going to be thinking about winding numbers, which are much smaller than 29, as August was talking about, where things got quite chaotic. So here we're also assuming that the condensate is well described by the Gross-Potevsky equation, or the GPE for short. And here I'm using the same conventions that August introduced during his presentation. So here we're working with units where the healing length is just equal to 1. So again, we've got this. And I should also mention that here we're going to be focusing on how the vortex decays due to dissipation of energy into the surrounding sound modes. So here we don't need to have dissipation in the system because we're really focusing on the vortex sound coupling. So again, we can write this Madelung representation for the condensate wave function, where this rho is the density describing the distribution of bosons in the system. And when we take the gradient of the phase of the condensate wave function, we get the velocity field, which is describing how the bosons are flowing. So for vortex solutions, if we're working in polar coordinates, where theta is the angle about the vortex axis and r is the distance from the vortex axis, then the vortex velocity field is just going to decay as 1 over r, and this proportionality constant is precisely the winding number, which can only take on integer values due to the fact that the condensate wave function has to be continuous. So for L equals 0, we've got no vortex. For L equals 1, we've got a singly quantized one, and for L equals 2, we've got a doubly quantized one. And I'll only go up to L equals 2, a doubly quantized vortex, in what I'm going to talk about. So now we've got a velocity field for the system, but we need to solve for the density. So we can do this by solving this the stationary GPE numerically. So we've got some examples of this on the right-hand side here. The kind of trapping potentials that we're considering are these hard wall kind of bucket traps, which are just smoothed out for numerical purposes. But if we go ahead and solve the GPE for this kind of trapping potential, then the kinds of density profiles that we get are shown here as these 3 curves. So when we've got no vortex, the condensate density is uniform throughout the bulk of this trapping potential. And then at the wall of the trap, it's going to drop to 0, and it's going to be 0. It's going to be pretty much 0 outside of the trap wall. The only difference then when we have a vortex in the center is that the density is also going to drop to 0 on the vortex axis. So this blue curve here is a singly quantized vortex, and the green one is a doubly quantized vortex. So what we can see is that as we're increasing the winding number of the vortex, the size of this core region is going to increase. Okay, so that's the system we're thinking about. And now we want to see when the system becomes unstable. So we need to study the linear equations of motion and see if we get any unstable modes. So in order to do this, we first of all start by perturbing the condensate wave function. And then we can exploit the properties of the vortex, specifically that we're working with a stationary solution as our background, so we can split into the different frequency components. And the vortex is also symmetric about its axis, so we can split again into the azimuthal components. So that's these M's here. And if we do this and then we insert this into the GPE and we linearize, we obtain the Bogoliubov-de equation, which can be written in compact form, which is this equation here on the left-hand side. So here we've got this L, which is a differential operator involving some radial derivatives, and this is going to act on the state of the fluctuations, which is really just a combination of these radial wave functions, which are encoding the radial dependence of our fluctuation field. So the name of the game in a moment is going to be to try solve the Bogoliubov-de equation for particular trapping potentials with a vortex inside of it. But before moving on to do that, it's useful to note that that the BDG will conserve a quantity called the norm, which is basically a measure of how much. It's basically a measure of the particle content contained in a particular omega M mode. And it also conserves the energy, which is just the norm multiplied by the frequency of that mode. So what's going to be really useful for us is this conservation of of the energy here. Okay, so now let's go ahead and solve this equation. The way that we can do this is we can introduce a discrete radial grid, and we can make this differential operator just a matrix. We then solve this matrix for its eigenvalues, which are the frequencies, and the eigenmodes are then going to be these radial wave functions here. So let's start simple and do this for the singly quantized vortex. And just to remind you again, the reason that we're doing this is we're trying to see if the system has any unstable modes in it. So when we do this for the singly quantized vortex for the m equals 1 mode, we obtain the following plot here, which is just the dependence of the different eigenvalues, which are the frequencies, on the size of the trap that we have. And over here on the right hand side, we've got some examples of what the corresponding eigenfunctions look like. So here I'm just superimposing the eigenfunctions over the corresponding eigenvalues so that we can compare them all. So what the colors are indicating here is that the eigenvalues that we're getting can be split into two different categories of solutions. So first of all, we've got the curves that are shown as black here. And these correspond to phonons that occupy the bulk of the condensate. So they live outside of the vortex core. And the reason that we can see this is if we look at the corresponding eigenfunctions, then we can see that we've got some oscillations basically away from r equals 0, which is where the vortex is located. So these are fluctuations that live in the bulk of the condensate. Another reason that we can identify these as phonons is because if we remove the vortex from the system, then it would turn out that all of these modes that are colored in black would still be in the system. They'd just be displaced slightly by the fact that the vortex is no longer in the system. And an important point here is that when we compute the energy of these phonons, these turn out to have positive energy. So the next kind of solution, of which there is only one per trap size, is the one that's shown in red here. And it turns out that this corresponds to an oscillation of the vortex core itself. And the reason that we can see this is because if we look at the corresponding eigenfunction, we can see that this is strongly localized, on the vortex axis itself. So this is this mode, which actually has negative energy, is describing an oscillation of the vortex core itself. And the reason that this mode has negative energy is because this mode is trying to lower the overall energy of the system. So you might have heard before that a singly quantized vortex placed inside a finite sized symmetric trap will actually prefer to precess about its axis. Or a lower energy configuration of the system will be if the vortex is precessing about the origin. And this is precisely what this negative energy m equals 1 mode is describing here. Now, a key point here is that because we're working in a system which is dissipation free, there's actually no way to excite this negative energy mode. Because normally if we had dissipation, that would lower the overall energy of the system. It would force the system into its ground state, which would correspond to a vortex precessing about its axis. But here we're working with a dissipation-free system. So this mode won't be excited. And the singly quantized vortex in a symmetric trap will just be stable. Now things get a little bit more interesting when we look at a doubly quantized vortex. So here we're looking at the eigenmodes that correspond to the m=2 mode. And in this plot on the left-hand side, we can see that we've got qualitatively the same kinds of solutions. We've got the phonons, which are shown in black, and then we've got this vortex mode, which is shown in red. But the key thing here is that for specific trap sizes, this phonon mode can actually, the vortex mode can actually couple to one of the phonon modes, depending on the size of the system that we have. So when the vortex oscillation comes close to one of the phonons, when it comes close in frequency, the two are going to couple together to produce an unstable mode. And the reason that we can see that this mode is unstable is because the imaginary part of the eigenvalue actually becomes positive. So this mode is going to correspond to a mode which grows in time. And if we want to think about our radial eigenfunctions, then first of all, what we've got here is we've started on a trap size where the two modes, where phonons and the vortex mode aren't coupled to each other. So here we've got a trap size which is 23 healing lengths. So over on this plot here, this is somewhere up in this region. So this is the vortex mode isn't yet talking to the phonons. But now if we increase the trap size slightly so that these two frequencies come close together, what we're going to see is that these two modes combine to produce a single unstable mode. So that's what's happening there. And yeah, the final important point here is that what this unstable mode is describing. Oh yeah, sorry. So if we go ahead and compute the energy of this unstable mode, it turns out that it's got 0 energy. And the reason for this is that the part of the mode which is localized in the vortex core has got a negative energy, but the part that's out in the bulk of the condensate has got a positive energy. And if we integrate over the full mode, it turns out that the negative energy part and the positive energy perfectly balance to make the total energy of the mode equal to 0. So because this mode costs 0 energy, that's why it can blow up and grow exponentially in time. And what this is then describing is it's describing removal of energy from the vortex configuration and the depositing of this energy into one of the surrounding phonon modes. So as this instability is growing, what this is doing is it's siphoning energy off the vortices and depositing them into the surrounding phonons. Okay, so we've now seen that this doubly quantized vortex is going to be unstable. It's going to have a mode which exponentially grows in time. But why should this mode make the vortices split up? So we can get some intuition for this by going back and considering the point vortex model, which August introduced in the previous presentation. And for two vortices, which our doubly quantized vortex is going to decay into, this point vortex model is particularly simple. It just tells us that each vortex will move under the influence of the other one's velocity field. So what we can do is we can go ahead and solve this system, and we can write a solution in terms of the difference of the two vortex positions. So this d parameter here is just the modulus of the separation between the two vortices, and this omega is the orbital frequency of the vortices around each other. So we can see that this solution is describing two vortices which will orbit around each other at a fixed distance d, and the frequency that they orbit with is proportional to 1 over the square of the separation between them. So what this means is that two vortices which are close together are going to spiral around each other very quickly, and then as they move apart, they're going to spiral slower and slower. Now, the key part in this argument is that if we go ahead and compute the energy of the vortices within the point vortex model, then the dependence of the energy on the vortex separation is given by the following here at the bottom. So we can see that as we increase the separation between the two vortices, this is going to lower the energy of the system. So now we go back to our instability and recall that the growth of this instability was describing removal of energy from the vortices, and it was dumping this energy into the phonons. So if energy is being removed from the vortices, then what this point vortex model is telling us is that the vortices will respond by separating and increasing the separation between them. So this is really the reason that the vortices will respond to the instability by splitting up. Okay, so now we've argued that a doubly quantized vortex is unstable. And we've argued with this point vortex model that we expect this instability to split the vortices up. So now what we want to do is perform some numerical simulations and see if we can actually observe this unstable mode growing before the vortices then split up. And what we're expecting to see is a large m equals 2 phonon surrounding the original vortex. And eventually we're expecting the end state of the system to be 2 well separated vortices. So let's see if we can see that. So what we've got here is it's a numerical simulation, which is prepared. We've got a symmetric bucket trap outside of which the density is approximately 0. So that's this dark blue region. And then on in the center, we placed a doubly quantized vortex, which is why the density is dropping to 0 at the origin. And what I'll do is I'll let this play 2 times. It might be a little bit laggy. So when I let it play the first time, I'll let it play through uninterrupted. But then the second time, I'll pause at some of the key points and I'll point out the things that we're looking for. But just to remind you, what we're looking for here is to see how this unstable mode grows as the vortices are trying to split up. So I'll press play. So at the beginning, we don't see much because the instability is small, but then we start seeing some blobs outside in the bulk of the condensate. The vortices then split up, which is what we expected, but then completely unexpectedly, they go back together again and stay together for a bit. And then they separate again. And then they go back together again. So when we first saw this, we were really perplexed by it because, as I mentioned before, we expected to see that the end state of this instability would be 2 well separated vortices. But instead, it seems like the separation between the two can actually undergo these strange modulations. So I'll just play this through one more time and I want to point to a few key things. So again, instability is small at the beginning, but then at some point it becomes fairly large. So here we can see these patchy regions outside in the bulk of the condensate. There's 2 of them. So this is this m equals 2 phonon I was talking about. And you may or may not be able to see that this core region has also picked up some an m equals 2 deformation. So this is corresponding to the vortices trying to split up. Once these vortices have separated, so we argued before from the point vortex model that 2 separate vortices is a lower energy configuration. Where is this energy gone? Well, these patchy regions outside in the bulk of the condensate are now much more pronounced. So the energy of these phonons has increased. And then, we went back to the beginning. That's a shame. Then when the vortices go back together again, these patchy regions have now disappeared. So what we're expecting to see here, once we go ahead and perform some computations on our numerical data, is that the energy of the surrounding phonons should decrease when the vortices go back together again, because this is increasing the energy configuration of the vortices. So we'll come to that in a moment. So just a few more plots to illustrate what was going on in those simulations. On the left-hand side here, we've got a plot of the phase of the condensate wave function. So we start with a doubly quantized vortex in the center. So we've got a single singularity in the center around which the phase is wrapping twice. So this is the double winding of the vortex. And at some later time, this then splits in 2. So around each of these singularities, the phase is just wrapping once. So these are our 2 singly winded singularities. This central plot here is just the density, which I was displaying in the simulations a moment ago. And then this panel here is just the difference between these 2 panels. So this is showing that that we've got this pronounced m equals 2 mode localized on the vortex axis. Now, the real interesting thing is in these plots over here on the right-hand side. At the top, we're showing how the separation between how the modulus of the separation between the 2 vortices varies as time goes on in these simulations. And in the bottom plot, we're showing the logarithmic amplitude of this m equals 2 mode localized on the vortex axis. So we can immediately see from these to, by comparing these two plots, that as the m equals 2 mode on the vortex axis is growing and then decaying, that corresponds to the vortices moving out and then moving back in together again. The second very interesting thing from this is that what we're displaying here is how the separation modulations evolve in time, depending on the size of the trap that we have. So this orange curve here is a trap size which is 25 healing lengths in radius. So that corresponds to the simulations that I just showed a moment ago. This green curve is a trap which is slightly larger, and the blue curve is a trap which is slightly smaller. And by slightly, I mean less than a healing length if we look at the numbers that are down here. So it's very interesting that although these separation modulations seem to be a very persistent and robust effect, the form that these modulations take and then the timescales associated with them seems to be heavily dependent on the trap size that we have. So unfortunately, we don't have a rigorous quantitative theory for why that will predict the timescales and then the form that these modulations will take. But we do have some qualitative intuition as to why they're occurring. So first of all, I mentioned that there's this energy exchange between phonons and vortices. So to quantify this, we can estimate the kinetic energy of our condensate. And then we can split this into the compressible part, which is representative of the phonons or the sound waves. And then this incompressible part, which represents the vortices. And if we plot these two different parts, which we've done over here on the right-hand side, then we can see that as the energy of the sound waves is increasing, the energy of the vortices is decreasing. And then similarly, when the energy of the sound waves decreases, the energy of the vortices goes back up again. So this is clearly indicating that there is this back and forth trading of energy between phonons and vortices. So the qualitative reason, or the qualitative reasoning that we have for the existence of this phenomenon at the moment goes as follows. So it starts by recalling that the origin of this instability was the coupling of a core vortex mode to a bulk phonon mode. So when back a few slides ago, when I showed these eigenvalue plots, there were two classes of solutions. There were the red ones, which were the negative energy vortex oscillations, which were localized at R equals 0. And then there was the positive energy phonon modes, which lived in the bulk of the condensate. And we got an instability when the two frequencies of these modes was close together. And then these two modes actually coupled together to produce a single unstable mode. Now, because this mode's unstable, it's going to exponentially grow in time. And eventually it's going to hit the nonlinear regime, at which point the vortices are going to try separate. Now, from our point vortex model, we're anticipating that when the vortices separate, the orbital frequency of those vortices is going to decrease. But it's precisely the core part of this instability that is the vortices splitting up. So if the orbital frequency of the vortices drops, then we expect the frequency of the core part of this unstable mode to also drop. And if this frequency drops enough, then it will actually decouple from the phonon mode that rendered the system unstable in the first place. And provided that the density of phonon modes is relatively sparse, which it will be for a sufficiently small system, then this vortex mode won't be able to couple to any phonons of lower frequency. So at this point, the system will be stable and the vortices will stop moving apart from one another. So this predicts, or this explains, it gives us some qualitative intuition as to why the vortices stop moving apart after a certain time. Now, the reason that they come back together again is a little bit more subtle. And it goes back to the fact that the linear equations of motion, or I should say that the complex conjugate of this unstable growing mode is also a solution of the linear equations of motion. And the complex conjugate of an unstable growing mode is just a stable decaying mode. And if we think that this unstable mode was making the vortices move apart, then what this stable decaying mode is doing is it's bringing the vortices back together again. So the linear equations seem to encode the fact that the vortices can come back together again, but now we need to explain why this decaying mode is actually being produced at some point. And the reason for this is that, or the reason that we think it is that the difference between the unstable growing mode and the stable decaying mode is that the bulk part of the mode, which corresponds to the phonons, shifts by a relative minus sign between the two modes. So I've tried to illustrate this schematically between these two plots, which is shown in green. So this one here was the unstable growing mode, and then this one on the right hand side is the stable decaying mode. And the reason that we can produce this stable decaying mode is that once the core mode and the bulk mode have decoupled from each other and are oscillating at different frequencies, we're going to gradually accumulate a phase shift between the two. And after sufficient time has elapsed, this bulk part of the mode will have changed by a relative minus sign, at which point these two modes can come back together to produce this decaying mode, and that's going to make the vortices go back together again. So this is our qualitative understanding of why these separation modulations are occurring in the first place, but it's not a quantitative theory, and in particular, it doesn't predict the timescales associated with these modulations or the shape that the modulations should take. So this is something that we're still working on, and we hope to figure out soon. The last thing that I just want to mention quickly is that you might wonder, is this a case of fine tuning? Do we have to set particular system parameters to see this? The answer is it's not necessarily a case of really fine-tuning the system. So, for example, we find that it's not actually unique to having a doubly quantized vortex. We also see it for a triply quantized vortex, and in that case, the vortices can split into a triangular lattice, and this lattice will basically pulsate in and out as the vortices are orbiting around each other. It also still occurs if we slightly displace the vortex from the center. And probably the most important one is that we still see that this effect is occurring somewhat if we add a small amount of damping to the system. So adding damping to the system is going to mean that energy is removed and vortices are gradually going to drift apart from one another. But provided this drift or damping is small enough and this drifting is slow enough, what we actually see is that the vortices will, the separation between them will modulate as they're gradually drifting apart, provided that damping is small enough. So this means that we might actually be able to observe consequences of this in an experiment. Okay, so that's everything that I wanted to mention. Just a brief summary. We started by arguing that vortices are linearly unstable, and that this instability resulted from the coupling of a negative energy vortex mode to a positive energy sound mode in the bulk of the condensate. It's the negative energy part of this unstable mode that makes the vortices split. And then counterintuitively, we saw that in a finite size system, the phonons can actually transfer energy back to the vortices and make them go back together again. And this really goes against our expectation that the end state of this instability should be well-separated vortices. So with that, I'd like to thank you for listening and open the floor to any questions.
Thanks very much, Sam. So we raised your hand. Just
yeah, I have two comments essentially. Very good talk, Sam. I liked it very much. The first question is, what would happen if you use absorptive boundary condition instead of using a potential, at the boundary? If you use absorptive boundary condition, you can take away the sound waves emitted from the center. In that case, will the two vortex simply just separate?
Yes, I think they would. So if we have absorbing boundary conditions, this is akin to, or it's another way of imposing really an infinite system, because sound can just leak out of the system as it would go off to infinity. In that case, okay. What happens, which plot am I looking for? I guess this one will do. In an infinite system, the spectrum of sound modes or the spectrums of phonons outside the vortex core is effectively going to be continuous. And because of that, the thing that was causing these separation modulations was that the vortex core mode decoupled from one of the phonons, but then the phonon density of states was sufficiently sparse that it didn't then couple to the next lowest one. So that meant that the only thing it could do was recouple to the one that made it unstable in the first place. But at that point, they phase shifted and it produced this decay mode, which made them go back together. This wouldn't happen if the density of phonon states was continuous, because this negative energy vortex oscillation would be able to couple to the next lowest available phonon. So it would always have a channel that it could radiate energy into at that point. So I think it's really a case of having a finite size system with reflective boundary conditions. Okay,
this makes perfect sense. But then something I'm very interested in is, what if you, instead of considering a doubly charged vortex, simply just considering a cylinder that carries two quantized circulation. Now, my imagination is there probably exists a threshold diameter of the cylinder below which the circulation probably can escape. But if the cylinder size is large enough, probably the two circulation will be simply trapped by the cylinder. So that's something I feel quite interested. Yeah, I mean, your theory model probably can provide an answer to us.
Yeah, I'm not sure. We haven't looked at that. I guess that would be akin to. It sounds like circulation. If there's a cylinder around which we have circulation, that would pin. I guess that would pin the vortices. But I guess if the cylinder was small enough, then maybe the flow could. We could get some vortices sort of moving off that internal boundary, but I guess if it was large enough, then the flow would be moving slow enough against the boundary that you couldn't produce a vortex. I'm not sure, but it sounds like yeah. I think I would agree with your intuition, although I haven't looked into it properly. But
yeah, I think this probably would be true even for multiple charged circulation, on a cylinder.
Yeah.
So it would be interesting to investigate this if possible. Yeah.
Well, actually, sorry, I just thought of something in the meantime, that if you have a very large cylinder, then you're effectively blocking out the region of the flow where this negative energy mode exists. So I guess there's probably going to be a critical size above which this negative energy mode won't actually live in the system. And that's a crucial part of why this instability, why this phenomenon is happening. So I think that should be why it wouldn't occur for a large enough cylinder, because you wouldn't have this negative energy mode in the system.
Yeah, the size probably depends on the number of circulation, right? So it would be interesting to work this out.
Yeah.
Davide.
Yeah, thank you. Again, another really interesting and beautiful topic. I remember listening to a talk that was maybe 4 or 5 years ago from some Japanese group. I think it was maybe Kobayashi or someone else, like a former student of Makoto Tsubota, and they were talking about a problem similar to those. I mean, on how multiply-quantized vortices will split. And I remember that they were talking about two different types of instabilities. One was like a dynamical instability, and another one was an energetic type of instability. And they were also mentioning, I remember, maybe a previous work done by, I think, a Swedish group about looking at this type of problem in a trapped or on a confined geometry. So I wonder, well, first, if you're aware of these works and how do they fit with your let's say explanation and Bogolyubov de Gennes study. I mean, which I really like. I mean, so I really like this idea of viewing this instability in such a way.
So I think what I've been discussing here is the dynamical instability, because this is what dynamically arises in the absence of dissipation from the coupling of the vortex mode to one of the phonon modes. I think the energetic instability is when you have damping in the system, and this. So, for example, I mentioned that the singly quantized vortex has this negative energy mode, but this isn't a dynamical instability, because unless there's damping in the system, there's no way for this mode to be excited. It's only if you then add damping or dissipation, that dissipation will remove energy from the system, and this negative energy mode will be excited. So this is an energetic instability. What we have was a dynamical one for the doubly quantized vortex, because even in the absence of dissipation, this will just spontaneously be excited. So it's dynamical. And sorry, so you mentioned something about the role of geometry or something.
Yes, yes, and I remember, I mean, in this talk they were mentioning some previous work about the fact that somehow you can have, for example, that multiply quantized vortices are stable in a confined geometry.
Ah, yes. Okay, so this is precisely what this plot here is showing. So for a specific size trap, so the size of the trap is going to determine the frequencies of the phonons that live outside the vortex. Just like when you solve the wave equation in a cylindrical trap, you get Bessel functions, and the eigenvalues is just some discrete set of frequencies. And as you increase the size of the cylinder, the frequencies become closer together. So this is precisely what this plot here is showing. It's as we increase the trap size, the phonon frequencies come close together. The oscillations of the vortex mode is really a characteristic of the vortex itself, which isn't affected by the boundary. So that's the reason that this mode is staying approximately constant as we vary the vortex size, as we vary the system size, sorry. But you can see that it's only for particular size systems, for particular trap sizes, that this vortex mode is going to overlap with one of the phonon modes. And it's when you have this overlap that the system becomes unstable. So for example, if we pick something that was a trap that was 10 healing lengths, or just sort of in this window here, then we're suppressing that coupling between them just because of the frequencies that those phonons have. So you have to pick a particular trap size so that these two types of modes are coupled to each other. Yeah, and another consequence of this is that as we take the size of the trap off to infinity, the density of phonon states is going to become effectively continuous. So this vortex mode will always be able to couple to something. So it's really a case of having a trap which is small enough that that the phonon frequencies are quite well separated in order to stabilize the system.
Okay. Thank you for re-explaining that. Now it's much clearer to me. Thank you.
Towards the end, you tried to address kind of seeing this experimentally. How sensitive is what you're seeing to noise? So if you added some noise to the system, do you still see this recombination?
Yes. So I think it's basically a case of the characteristic damping time has to be much longer than the characteristic instability time.
Well, not damping, but just sort of having some phonons that you excite in the system just due to sort of experimental effects, rather than actually explicitly through damping.
Yeah, I see what you mean.
Sort of 1% of noise on your kind of initial condition. Do you still see?
Yes, I think at that point the instability will just grow out of the noise, because the noise is just going to be a superposition of all the normal modes in the system. You've got one instability and then or one unstable mode, sorry, and all the rest of the modes are, they're not going to grow in time. So eventually this unstable mode is going to grow out of the noise, would be my expectation. So but I suppose that's dependent on the noise being small enough, I guess, because if the noise is initially quite large, then the system is straight away in the nonlinear regime.
This is my wonder about, kind of, could you sort of put a constraint on the level of noise to sort of see if it's experimentally feasible?
Yeah, I mean, the honest answer is, I'm not sure. Someone's mentioned to us before that, so the normal way that you would create a multiply quantised vortex in a system is by phase imprinting, but phase imprinting is an inherently noisy process. You end up with a lot of noise in the system, and at that point, it's not totally clear that this perturbation, the theory kind of argument can be applied, and we're not totally sure at the moment, but maybe we could do some simulations to check that out.
Thanks. Time for any last questions? No, well, thanks to Sam and August for two really interesting talks. Just to say, our next scheduled webinar is now in a month. We did have a talk scheduled in a couple of weeks, but that's been rescheduled. So if anyone's got something they'd really like to communicate, some new results, we do have a slot free on the just bear with me, on the 29th of March. So if you're interested in giving either a full-length talk or a short talk there, please just get in touch. Otherwise, the next talk, and this will be communicated out in due course, is then on the 12th of April. So we'll see you back there if no one volunteers. Okay, thanks very much, everyone.